I've made videos on the evolution of spiders and of mantises, butterflies, and there are more invertebrates that I'm going to cover, like cephalopods. I mean, how could I not do those? But my real passion is vertebrate paleontology and zoology. I want to do a series of videos on that, beginning with the diversification of tetrapods, mammals, reptiles, birds, amphibians. But I guess before I can do that, I have to show the development of tetrapods first, emergence before divergence. All these most familiar fauna are chordates, meaning that our structure is based on a central support rod called a notochord, like the precursor for the spine, because the notochord runs along the spinal cord. Of course, it's not that way for everything. You see, initially, when animals first became multicellular, they had no kind of configuration at all. I mean, look at sponges. They're the first forms of animal life, and they don't know what they're trying to be. They're all over the place. All other animals that evolved later than sponges had some sort of body plan, but not sponges. What kind of plan do they have?
So what's the plan? Plan? There ain't no plan!
Sponges can reproduce sexually or asexually, and one sponge may be male and female at the same time. They're multicellular, but their cells aren't differentiated. They're made up of choanocytes, which individually are not much different than sperm cells, the most basic form an animal can take. In later groups of animals, choanocytes can be modified into epithelial cells, the first step of cell differentiation. And of course, different cells differentiate differently. Later groups of animals eventually happen across some sort of organization, falling into a body plan of whatever works. At the phylum level, animals branched into several distinct configurations, and some of those incidental arrangements worked out well enough to be modified into myriad subgroups. The others didn't work out very well at all and were doomed from the start, already going extinct early on with no living descendants. Because once there is a body plan, they can modify it and hopefully improve it little by little over time, but they can't change one body plan for another one. So if it doesn't work and it can't be fixed, then they'll just move over to the slow lane and dwindle into obscurity or extinction. At the phylum level, arguments for intelligent design look to me like a competition of different designers, most of whom aren't very good. Some animal body plans don't have any organs, none at all, and some of them don't even have mouths, and some that do don't have an anus. They eat and poop out of the same hole. And some animals don't even have a front and back. But in our case, we're pretty well organized, bilaterally symmetrical animals, and we're nephrozoan with a mouth at one end and an anus at the other. Well, not all the way at the end. Chordates added a tail that extends past the anus. Chordates first appear in the early Cambrian period, around 525 million years ago, branching off from other deuterostomes like hemichordates and echinoderms, though their apparent ancestors appeared in the fossil record much earlier, 555 million years ago, in the Ediacaran period, before the Cambrian. For a century or more, people thought that all the different phyla emerged at the same time in what was known as the Cambrian explosion, referring to what once looked like an abrupt proliferation of biodiversity in one layer of strata that they didn't have any ages for, neither how long ago it began nor how long it lasted. They named this layer of strata back in 1835, before the advent of radiometric dating. But what made this level interesting was that back in the 19th century, no one had yet found any Precambrian fossils, nothing below that level. So it looked like every one of these phyla just appeared abruptly, all at once, out of nothing. That's because that's when a few different lineages developed shells and other hard parts, making them easy to fossilize and recognize. And turns out there are fossils before then, too, but soft bodies require precise conditions to be preserved, and they're a lot harder to find because they're usually quite small. And they're weird, being much different than anything alive today. So they don't look like what you think you're trying to find. Thus, such fossils might take special equipment or at least a well-trained eye to be detected. And now that paleontology has progressed as a science, we find that not all phyla appeared in the Cambrian. A few were already evident in Precambrian strata in the Neo-Proterozoic era, and at least a couple phyla had already gone extinct before the Cambrian period had even begun, and another phylum didn't appear until after that period had already ended, more than 50 million years later. And by then, our phylum, Chordata, had already branched a few more times, producing the first fish. Although, what counted as fish back then were not what I think anyone would refer to as a fish now. Take picaya, for example. It is little more than a swimming worm that feeds with tentacles rather than teeth. In that sense, it's similar to lancelets that are still around today. Together, these represent the clade Cephalocordata. Their sister set, Vetulicolia, is one of the first prominent clades to face extinction in the Cambrian, evidently because they were so inefficient at swimming, eating, breathing, navigating, everything, apparently. And remember that at this point, deuterostomes weren't that far removed from proterostomes, most of which have exoskeletons. So before anything yet had an interior skeleton, Vetulicolians looked like they were trying to be the exoskeletal version of fish, which clearly didn't work. Their design was so bad, it's like their whole line was on a factory recall because they went extinct early on. They were evidently filter feeders, taking in nutrients from a permanently open mouth like a jet engine, and then filtering out some of that through holes in their sides, early gills. And we know that because the most primitive hemichordates alive today still have that same configuration. Likewise, some of what we think of as stationary filter feeders reproduce a nymph form that has the ability to swim to a new location where they eventually settle down. But one important lineage didn't. Some retained their tadpole-like nymph stage and they continued swimming. They were still filter feeders, taking in microbes as they moved along, and that takes more energy, and more energy means that they need more oxygen. But the type of filter feeding they were doing provided that too. These holes in their sides allowed water to pass through the filters, which of course incidentally allowed oxygen to be absorbed directly into their bloodstream. That is a hugely advantageous adaptation, facing profound selective pressure to improve on that trait. Vetulicolia weren't able to keep up, having to deal with a suite of other issues that they're trying to overcome at once, but their sister clade, olfactories, being already more efficient, were also more adaptable. As the name suggests, olfactories were a lineage of chordates whose interior tissues can detect certain types of molecules, giving them a sense of taste and, more importantly, smell. This is another hugely advantageous adaptation in that environment, so of course later generations lived with selective pressure to keep that up too. But then there's the other lineage, tunicates. As some of these are like tiny free-swimming plankton. Others went back to the old way of being a tadpole in their youth only until it finds a place to settle down and establish roots. Then they take on a different shape. One of the laws of evolution is that the young of two closely related organisms will look more alike than the adults do, reflecting how they started out the same but then grew apart. And tunicates illustrate this. They still have a notochord and a postanal tail and all that. They still look very much like primitive fish in their nymph stage, being active and mobile in their youth, but then they become sedentary and look quite different as adults. Yeah, I know. Some of us are the same way. The sister clade of tunicates are vertebrates. These two start out looking like tadpoles, but they never settle down. They'll take a rest now and again, but otherwise they don't stop moving until they die. What differentiates them is that their notochord only exists in embryo and is replaced by a segmented spine, although at this point the spine is still made out of cartilage, not yet bone. The subphylum Vertebrata begins with Mylocommingidae. They are similar to the swimming worm-like fish that we mentioned before, except that these appear to have a skeleton, however thin or sparse it may be, beginning with vertebrae descending from the beginnings of a skull. Although at this point their skull looks more like an ultra-lightweight bicycle helmet. But this is how such things develop. It still sufficiently envelops the central nerve system known as the brain. Thus, Mylocommingids, along with a handful of other closely related fossil forms, represent a transitional condition between basal olfactories and vertebrates, being the beginning of the clade or category of fish, true fish, what everyone universally accepts as a fish.
What's the animal in this world that you fear the least? Fish. Animal. Fish.
Don't
start.
Don't.
You're starting and I'm not.
A fish is an animal.
No, it's not. I'm talking about an animal, like a real animal. Like
Fish. Fish.
No,
Fish is
being
animal.
hard-headed. I'm talking about that's like saying like an ant. That's not an animal. Fish aren't animals. That's a sea creature.
What? It's a sea creature. A fish is an animal.
You can't go to the zoo and see a fish. They don't have zoo fishes.
There's actually so many fishes.
There's fish zoos? You can go to a fish zoo.
No,
Oh.
there's so many fish that they have their own f***ing attraction called an aquarium.
No, they don't. No, that's different. That's like sharks and shit. Those are animals.
Fish!
No.
Fish!
No, that's why they have different names. Sharks and fish.
Of course, fish is not a taxonomic term because there's no consistent definition for what a fish is. And people used to say that a fish is a cold-blooded vertebrate with fins and scales and gills, and that may be a typical fish, but a consistent definition will not have exceptions. There are plenty of fish, or vertebrates that everyone accepts as fish, that don't have fins or that don't have scales. And some fish have lungs, and some are even warm-blooded. And there are some vertebrates, both living now and in the fossil record, that are not considered fish, even though they're entirely aquatic and depend on gills. So having the gills of a fish does not make one a fish. Thus the word fish is paraphyletic, meaning all of these except for those, or alternately, all chordates except for tetrapods, because humans make arbitrary distinctions. But if we want a taxonomically consistent system of classification, then it must be monophyletic, phylogenetic. So we use the terms chordate or vertebrate or craniate instead, and everything from here on is all of the above. If we use the paraphyletic colloquial language, then the category of what everyone accepts to be a fish is a bigger group than you think, and not just because of everything that evolved from fish. Let's forget all about those for a moment, because all the fish that everyone accepts as a fish that are alive today ultimately fall into very few categories compared to what there once was, that have gone extinct long ago, even before the dinosaurs showed up. I'm not talking about coelacanth either, well, at least not yet. We'll get there. No, what I'm saying is that there were a lot more basic categories in the fossil record just in the first half of the Paleozoic era than we have today, probably more than you've ever heard of. Mylocomyngiids and their ilk must have had a difficult time swimming because they only had a pair of tail flukes running the length of their bodies, basically just a tail without any stabilizing fins. And some had to swim from side to side with constant torsion to keep them upright, which can be exhausting. The next clade on this chart, anaspids, began to correct for that by starting to develop additional fins. Anaspids are not a single species. And remember that there are typically multiple species within any given genus, and multiple genera within a taxonomic family, and multiple families within an order, and multiple orders within a class. And look how many species are in class Mammalia, for example. According to this website and its slightly antiquated Linnaean construct, Anaspida is not a species, it's a class, containing at least 2 orders with several families, each with multiple genera, leading to many species. And these are just the ones found in the fossil record, which, because of the rarity of fossilization, reasonably only represents about 1% of everything else in that class that we haven't found fossils for. When an animal dies, it usually doesn't fossilize. It's either torn apart or swallowed or decomposes, turning into dirt. In order to be fossilized, it has to be sealed in a protective layer of mud or tar or volcanic ash before it rots away. It's very rare for that to happen, yet fossils are found all over the world. And most of them are buried deep where we're not likely to ever know about them. The first mosasaur fossil, for example, was found 90 feet deep in a Dutch quarry. Think about how deep a hole that is. And they just happened to dig that there because it's a quarry. Now imagine what might be 90 feet below where you are now that no one will ever find, that'll remain hidden forever because no one's going to dig a 90-foot hole there. Once fossils are exposed to the surface where we can recognize them, they are immediately subjected to erosion and may be ruined if not found quickly. So you have to look at the right place at the right time to find anything at all. Yet we've still found millions of them. Imagine how many more have to be out there somewhere. So in order to find any fossils at all, you'd have to have huge populations living for many generations, and we have thousands of species represented. So there were a lot of them, and they were around for a long time. Some anaspids only have a tail fluke, although on most of them, that one fluke is developing into 2, one up, one down. Some also have distended gill bars. And some of their fins stretch all along the back, usually in the form of a dorsal ridge. And some of those dorsal fins seem to be having developmental problems. This is why paleontologists see evolution as a never-ending series of blind trial and error experiments. All these fins are along the top or the bottom, but a couple of these very primitive fish have side fins, something an intelligent designer would have put on all of them straight away. The leading edge of this fin begins with a little spike, just like what they have above and below, and a Hox gene duplicated that spike on the other end. The performative significance of these is only apparent when that one side fin becomes two separate fins that can move independently. But we're not there yet. It'll take a long time to get from this to pectoral fins and pelvic fins. Until they have and can use pectoral fins, any attempt to accelerate in their current configuration would only cause them to nosedive to the bottom, where they have to spend most of their time anyway, being as all these early fish had to eat by sucking tiny organisms out of the sea floor. And not the deep sea either. They hunted by eyesight, and they hunted things that depend on the light, so they had to stay along the shorelines. And we're not in the Cambrian anymore. Anaspids appear throughout the Silurian and Devonian periods, but not in the Cambrian or Ordovician. That means there were other earlier forms, precursors to this group that we haven't identified yet. Maybe Mylocommingiids, maybe something else. Curiously, as primitive and poorly designed as anaspids were, most of the fish we're about to see were even worse. The next clade of anathans, or jawless fish, were much more primitive than anaspids, and they're older, appearing in the Cambrian. They also lasted longer until the Jurassic, but they went another direction entirely. This group begins with conodonts, eel-like biting worms of the deep, because while they didn't have jaws, they did have teeth, scary teeth. They were different from the teeth of anything else that has teeth because they evolved independently and work differently, more like a saw than a clamp, and they're mounted in the sides of the mouth rather than above or below. Conodonts don't exist anymore, but the next clade does, and they're similar. Cyclostomi consists of hagfish and lampreys, the only jawless fish that still exist. And they're very much like conodonts used to be, kind of like the oceanic version of maggots writhing through fallen carcasses. Lovely image, isn't it? Interestingly, hagfish are classified as vertebrates even though they lose their rudimentary vertebrae in early development. They grow up without a backbone, which, well, they didn't have bones to begin with, but they grow up without a spine. And this makes them even more maggot-like. In a sense, hagfish and lampreys and conodonts are technically fish, but just barely. Not what most of you would consider fish, certainly nothing you'd go fishing for. The next clade, however, and all the clades from here on, do get progressively fishier, but it doesn't happen quickly. Pterospidomorphs are almost as old as conodonts, dating from the late Cambrian through the Ordovician and Silurian up to the late Devonian. Imagine what all the predators were like for most of that time. Initially, the only predatory fish around were conodonts because those were the only fish that had teeth. They're also more inclined to be scavengers, eating what is already dead, so really there were no predatory fish at all. Not even sharks existed yet, not this far back. But there were orthocones, massive mollusks with biting beaks, and there were eurypterids, giant semi-scorpion-like sea monsters the size of alligators. And in both categories, there were also smaller versions, and crustaceans too, all with biting and pinching bits. So in this environment, it made sense to be shielded in armor, and pterospidomorphs were. They were armored head to tail, which had to make swimming difficult, and only possible in short bursts. And without pectoral fins, those bursts must have been chaotic. It's probably why they had the armor in the first place, because they couldn't swim for crap. It's also interesting that their scales were made of bone, just like the scales of modern fish. Their armor plates were made of bone too, but their skeletons were not. Their skeletons were still made of flexible cartilage. At this time, calcium was reserved for the outsides of their bodies. As you can see, there were several varieties of these too, and of the next clade as well. Class Telodonti consists of multiple orders with at least a couple dozen families, so they're quite diverse. They're not armor-plated in the same way as pterospidomorphs were. Instead, they're similar to anaspids, but coated in a unique form of dermal scales, and not like those of modern bony fish, but more like those of sharks, but even raspier, more coarse and abrasive. Beyond that, they're distinctly different from any fish alive today. They still don't have jaws, but now they have teeth. Well, not real teeth, but rigid projections that work like teeth. So they're biting their food. They just can't bite it very hard, only enough to grab it and suck it in, because their mouths could only open or close with the strength of their lips. That's not much of a bite. Here's a weird one. The tail and dorsal fin have become one large apparatus. Did they move independently? That'd be interesting. One has to wonder how this thing swam. It must have had ballast of some kind, because it doesn't look like it could sit on the bottom, and it still doesn't have any pectoral fins, so it couldn't swim properly either. But most of the other fish in this clade do have pectoral fins, of a sort anyway. Though I don't know how well they could move or how effective they were. They certainly weren't as flexible as the fins of modern fish today. Next up is a clade called Galeospida, a group known as the helmet heads. They're another taxonomic class consisting of a few orders of a couple dozen families of fish from the Silurian period. They're another set with full armor. Judging by the shapes of their helmets, these animals must have sat motionless on the sea floor, waiting to suck in whatever swam or crawled close enough. The wings or spikes on the side of some of these apparently helped against attacks from giant arthropods at that time. It's possible they could have helped in swimming a bit too, though not by much. Fins have to be able to move, and these flared blades in their armor can't. This next group, Paturiaspida, is only known from a couple of species, and then only from their ridiculous helmets, which in this case have a jabbing point in the front. The shape of the helmet implies that it could move fast, but the fact that it is still armor and in this shape implies that they were at rest on the sea floor most of the time. Our next clade is Osteostraci, also colloquially known as ostracoderms. This is our fourth separate taxonomic, albeit Linnaean, class of armor-plated, bottom-feeding, jawless fish. And they're just as weird as all the others. But some of them have pectoral fins that apparently work. And it seems that their primary function is to get these armored fish off the sea floor in a hurry and then guide their flight through the water and aid in their gentle descent on a new landing site. These guys didn't show up until the Devonian period, the late Devonian, around 432 million years ago. Remember that the first true fish evolved in the late Cambrian, almost 530 million years ago, which means that it took nearly 100 million years for fish to learn how to swim. And these are some weird designs. What am I saying? It is inappropriately polite to call this a design. This simply cannot be intentional. There is no indication of intent of purpose. These are obviously incidental adaptations to the after effects of accidents. This did not go according to any plan.
Right, no plan!
And probably nothing illustrates the notion of unintended incidental design better than this next most important adaptation of the vertebrate lineage. And notice how all these early fish had a series of gills along each side, like sharks have. The bass or trout that you catch at the lake have a series of gills too. It's just that most modern fish have these covered by a protective plate. That plate conceals a series of rigid gill bars. A primitive fish had more of them than modern fish do. The opening and closing of the mouth is in sync with the movement of these gills in order to draw water through. If the foremost gill bar is close enough to the mouth, then the same muscles move both. In this illustration, the green gill bar is what became the jaw, and the red one is what became the hyoid apparatus. When these are empowered by the same muscles to move together as a unit, then the muscles that close the mouth are attached to that rigid gill bar, and it becomes a jaw. Then the animal gets a new superpower. Now they can bite, hard enough to do damage, and that changed everything. Thus began the new clade of Gnathostomata, vertebrates with jaws. Now, obviously, there was some overlap in the biological connection between all these groups, like between jawless, armored osteoderms and the subsequent biting placoderms. And this is yet another whole taxonomic class of armored fish. Again, most of the armor is on the head, but at least some of them have fins that are able to swim properly. And the shape of their helmets reflect this. They're no longer flat on the bottom for sitting on the bottom. No, these are rounded and imply that these were perpetual swimmers. Apart from hagfish and lampreys, every fish that is still alive has jaws, and they must have been derived from one of these initially armored predecessors, what we now call placoderms. This is the group that has the first real teeth, the kind of teeth we still have. Not all placodonts had teeth, though. In fact, the most famous of this whole group did not. Dunkleosteus was a big old beast who took advantage of those jaws with massive bite force. In all of paleohistory since, very few animals could bite harder than this thing could. And it had a can opener for a face. Because instead of teeth, it had shearing blades like an industrial cutter, like the jaws of life, but, of death. The very first jaws of death. This, I think, is why having armor on fish in the Silurian period was a bit like having tail fins on cars in the 1950s. Why have it at all if it's not good for anything? Because when something like this specializes in slicing through armor plating, then you'd be better off dropping all of that dead weight and trying to swim faster than this thing or outmaneuver it. That's apparently what happened because placoderms were the last lineage of armored fish. Once the predators had jaws and teeth, wearing armor was no longer helpful. In fact, it would more likely get you killed. Dunkleosteus may have been the most impressive placodont, but maybe not the largest. There were a couple other close relatives like Gorgonithes, which was almost as bad. It still had shearing blades instead of teeth, but notice the reduction in the armor. Then there was Titanichthes, which, like many giants, was a filter feeder. The next clade to look at is Acanthodii. These start to look like familiar fish, but they're still not. It's like once they got pectoral fins, they suddenly had too many fins. I mean, come on now. Acanthodians are classified as stem sharks, leading to the clade of Chondrichthyes, the cartilaginous fish. One of the pet names for this group is spiky sharks, because some of them have spines just ahead of their dorsal fins, just like some fossil sharks did. And notice also how the tail bends upward and is only fluked on the bottom. Most modern sharks are still the same way. The first sharks appeared over 400 million years ago, but stingrays and their ilk don't show up until 250 million years later, 150 million years ago in the Jurassic. If you want to know how that happened, there are transitional intermediates showing how one lineage of sharks became rays. Most rays and skates and that sort of thing hang out on the sea floor, just like those armored fish used to do. But after the end Permian extinction event, every one of those old armored fish were gone, and the seafloor was unoccupied, open to new tenants. And what is interesting about acanthodians being stem sharks is that some of these do look a bit like really primitive sharks, except that they have an operculum. That's the cheek flap that covers the gills in modern bony fish. Or some acanthodians have rays in their fins. Modern sharks don't have ray fins, but ancient sharks did, and bony fish still do. Sharks also have partially calcified skeletons. Well, the jaws and teeth, at least. So Acanthodii is another paraphyletic clade, which is obviously ancestral to cartilaginous fish, sharks and rays, but it might also include ancestors of bony fish. Because, as I have already indicated, the next clade to examine is Osteichthyes. These fish appeared in the late Silurian and developed a bit differently in that while sharks only calcified their jaws into bone, Osteichthyes ossified their entire skeletons, except for some of the joints, of course. As usual, every major clade typically divides into two subsets. For bony fish, those are Actinopterygii, the ray-finned fish like trout and bass, tuna, and so on, and Sarcopterygii, known as the lobe-finned fish. And living examples of this group include lungfish and the coelacanth that we mentioned earlier. So all the jawed fish, everything except hagfish and lamprey, every other fish alive today falls into just 3 classes, whereas we just covered more than a half dozen other classes that are now entirely extinct and have been extinct for hundreds of millions of years. They were already extinct before the dinosaurs showed up. And there were still plenty of paleofish that you've never heard of in the Devonian and the rest of the Paleozoic. And then the Mesozoic got a whole other collection of fish you wouldn't expect. And of course, sharks continue to evolve into interesting forms throughout the Cenozoic, too. So in the next episode, I could pick up where I left off in the late Silurian and go into the evolution of sharks or the evolution of ray-finned fish. And I'm sure I will later on. But for right now, in this series, I'm keen to have this next episode cover the lobe-finned fish, and then we will explain how they went from fins to feet.